Back up. All right. So the way that I like to proceed when it comes to the unit on chemical compounds is I like to talk about ionic compounds and then name them, and then talk about molecular compounds and name them. All right. So we're going to separate out these two types of compounds when we learn how to name them. All right. And this is review. All right. Today is 100% review. Monday we're going to talk about polyatomic ions, where we're going to talk about carbonate and sulfate and chlorate and nitrate. Again, you've heard of those. That's a little bit of a review. But then we're going to expand that group to learn a whole big new group of polyatomic ions. So there'll be fairly new things on Monday. But for today, we're just getting the basics down, that stuff that we call the crossover method and all that type of thing, in order to get back into naming and that type of thing. All right. Chemical nomenclature. Nomenclature is just a big way of saying naming system. All right. So it's the chemical naming system. And this particular naming system that we're going to learn first is called the IUPAC naming system. At the end of class, we're going to learn about the classical naming system. The classical naming system is essentially a naming system that was derived by, and as I always do when I mention his name, I'm getting the book out, that was derived by Lavoisier in the late 1700s. Lavoisier kind of systematized naming. Before Lavoisier, different chemists were calling the same chemical by different names, and no one was speaking the same term. So Lavoisier started the procedure into kind of making a systematic naming system, all right? And that classical naming system had been used until, I think the early 1900s, where chemists around the world decided to get together and form this group called the International Union of Pure and Applied Chemists. And what they do is every year they get together in Geneva, Switzerland. I'm sure it's a grand old party, and they sit down and they have meetings and they talk about naming. Wow, what an exciting thing, all right? Now, the naming system that they derived in the early 1900s is what we're going to start with here, all right? And it's a very straightforward naming system. It's not a big deal. But they're also responsible for naming the new elements, all right? We had the question about the 116, all right? And actually 116 has been discovered, so I've got to change my test. I'm just too lazy to change it. But we actually have, we've got 113, 114, 115 recently, 116. I think they're really close to getting these. Again, they're very short-lived things, right? They slam some other nuclei into it, try to make a big nucleus, and then it blows apart. It's very unstable. But for many years, they decided, the IUPAC decided, you know what, we can actually, by the looks of it, continue to synthesize these elements, so it makes no sense to come up with fancy creative names, so why don't we just name them based on the numbers in their atomic number? So, like, unilium, one, nil, 0. So unilium, not very exciting, is really 110. And unium, that's fun, right? 111, right? Bium, by 2. All right, you get the idea, all right? Then a few years after they initiated that, they realized this is really dumb. So what they did was they actually went back and they renamed a bunch of them in memory, honor of people that were very influential in chemistry. So again, this whole line, not 10 years ago, were all these funny things, right? It's funny. And then last must be 5 years, Rutherford, right? We know Rutherford. Dubnium, I don't know who this guy is. Seaborgium, Seaborg was a chemist out of California. Borium, Bor, yeah. We have Mendelevium somewhere anymore. Right down here, Mendelevium, that was one recently done, right? These were also un, nil, unium, or something crazy like that. So Mendeleev, Nobelium, the Nobel Prize. Lawrence actually worked with the Seaborg guy in California, Laurentium. Anyway, all right. So these guys decide that type of stuff. Yes.
Just like they were very unstable.
Yes.
Like the last one be like a noble gas. Wouldn't it be like...
Its electron configuration would be stable, but the nucleus, which is a completely different entity, right? We're talking about the nucleus is unstable. Remember when we talked about radioactivity and the nucleus blowing to pieces, right? Radon, all right, is a noble gas, but it is highly radioactive. The nucleus is unstable. Radon won't form chemical bonds very easily with things. Chemically, it's stable, but on a nuclear point of view, it's unstable. It blows apart, turns into a different element. So those are two completely different types of stability, right? We're talking chemical stability versus nuclear stability. Different things, okay?
Yeah.
All right. Okay, so let's just go over a couple of basic things to get ourselves back into thinking about how we come up with names and formula. And this is a term that I may have mentioned. Again, I can't remember if it was the morning or the afternoon class that I mentioned this to already. But this is a term that I like to use. It is the big chemist's way of talking about the charge on an ion. All right? So we know that ions, stable ions, have charges. And we know how to determine the charge on many stable ions, +1, +2. And that charge we call the oxidation state. And I will guide your eyes to them in a moment on your periodic tables. Again, you've heard of the term univalent. Un, you just saw it many times. One. Univalent means it has only one possible oxidation state. It can only have one possible charge. And then we have multivalent. There are some ions that can exist in more than one stable oxidation state. And I'm hoping this isn't new as well. We use Roman numerals to indicate which oxidation state that we're talking about for that particular compound, because we have to be able to distinguish between them. So let's get our periodic tables out, because now we're to the point where we're going to be using that table to find some numbers, to do some various things. So get your periodic tables out so I can guide you to where you are looking to find the oxidation states. And if you take a look at the little legend up in the corner, and I don't know if I have a copy of our periodic table kicking around because people have borrowed them all away. Anyway, it doesn't matter. I'm pretty sure the oxidation state is at the very bottom of the box. Is that correct? Very bottom of the box, it says oxidation state. So if you take a look at group 1, and I don't know, I think maybe I went through this exercise with one of the classes. I don't know if it was yours. Now, for my periodic table, it's right there in the right-hand side of this first line. But for your table, like I said, it is at the bottom of the box. So you should be noticing for group 1, it is 1, 1, 1, 1, 1, 1, 1. Plus 1. Loses 1 electron, it becomes plus 1. That's the oxidation state. And for group 2, it's 2, 2, 2, 2, 2, and it is plus 2. All right? And those we call univalent metals. They have only one possible valence or power to bond, right? And it is 1. All right? So the oxidation state is in the box, and for these guys here, very obvious, it is just one possible value. Same with group 3. If you take a look at group 3 all the way across the transition metals, 3, 3, 3, 3, and then at the very bottom, thallium has a possibility to be also 1. All right? If we take a look at some of our transition metals, and we're now going to look at these because there are so many chemicals that we use that have these metals in it, we're going to have to name them and be able to come up with their formulas. But if we look at things like copper, you'll notice 2 and 1, and nickel 2 and 3, cobalt 2 and 3, iron 2 and 3. If you look at manganese, it's got a whole pile of different oxidation states that are possible. In actual fact, manganese behaves almost like a nonmetal, because if you take a look at the nonmetals like chlorine, you'll notice it has a whole bunch of different oxidation states. Okay? Now, we're not going to worry about all these extra oxidation states for the nonmetals. We're not going to worry about it here in this course. In this course, I need you to think of the nonmetals as only being determined by their group. Notice fluorine, -1. It's going to gain 1 electron. Chlorine has a whole bunch of possibilities, but I want you to treat it just like fluorine. -1, -1, -1, -1. We will be dealing with the extra guys next year, okay? Same with group 16, -2, -2, -2, -2, -2, even though they have all kinds of different possibilities. All right? Okay? Actually, the negatives stop at where the metals become nonmetals. All right? So here, the metals, this guy actually does something a little different. Don't worry about it. The reason why these can have all kinds of different oxidation states, same with these guys, has to do with that sub-level thing I keep mentioning about. That our orbits are not simply 1, 2, 3. It's 1, and then 2 has 2 little sublevels we call S and P, and then 3 has 3 sublevels that we call S, P, and D, and 4 has 4 sublevels that we call S, B, D, and F. And there's different levels within the sublevels. Complex, complex, confusion, confusion. You don't have to worry about that right now. We'll do that next year. I will explain to you all of these extra oxidation states next year. Okay? All right? So you don't have to worry about them right now. I do need you to know you need to stop doing that. I'm easily distracted. All right. You just need to be able to find the numbers of these multivalent ones when we're dealing with the metals, so that we know which one that we're dealing with. So if I'm dealing with a copper that has an oxidation state of 1, I'm going to call it copper 1. And if I'm dealing with copper with an oxidation state of 2, I'm going to call it copper 2. Okay? All right. So let's just take a look at some of these, and you don't need to write this down. This is really just for information's sake to point out to you where it is. These are some old periodic tables that we used to use. So if we're talking about a univalent metal, I don't have to call that sodium 1 because there's only one possibility. I just call it sodium. And I need to know that sodium is going to have an oxidation state of 1. And same with zinc. Zinc's a transition metal, but it only has also an oxidation state that is 2. There's only one of them. So I don't say zinc 2 because there's only one possibility. I only have to put the Roman numerals if there's more than one possibility. So if I'm dealing with iron, 2 possibilities. There's iron 2 or iron 3. All right? And this old periodic table has a 6, and I don't like the 6. Does yours have a 6 on it? Does your iron have 2, 3, and 6? Good, because I'm not a fan of the 6. It's a very rare one. 2 and 3. Okay? When there's more than one oxidation state, it's been determined scientifically that one state is a little more stable than the other state. That it hangs around in nature a little more. Actually, given the right chemical situation, the other state will eventually turn into the more stable one. Given a right chemical situation, it'll actually turn into the other state. It'll trade an electron away. Notice that in your numbers as well, that there's a bold number. All right? And for iron, which one is the bold number? 3, which means the iron in the iron 3 ion is a little more stable than the iron 2 ion. All right? Given the right chemical situation, the iron 2 ion will will get rid of an electron and turn into the iron 3. But we can make iron 2 compounds. They will exist, you know, for an extended period of time. It won't completely disappear right away. I cannot make a magnesium 3 compound. It doesn't exist. And therefore, magnesium only has one possible oxidation state. Okay? Because sometimes we'll need to talk about which one's more stable. So we need to know that, that bold thing. Okay, so just put down here examples. Just put e.g. Even though we didn't write the other ones down, we'll go through of them here. And again, just e.g. And let's name these. So we're talking about the metals. The name's not changing. The question is, do we need Roman numerals or not? Do we need to distinguish between two possibilities? How many possibilities for silver? Yeah, Chelsea? Everybody said it? That's great. 1. So do I need the Roman numerals? No. So what are we calling this metal ion? A silver ion. All right? A silver ion. So this is just called a silver ion. Excellent. Copper. Taking a look at copper. More than one choice. Yep, we're getting some nods. So what's that one going to call? Let's go hands up on this. What's that one going to be called? Yeah, Christopher? It's a copper 1 ion. Copper brackets 1 ion. All right? So when you're given, especially a transition metal, you've got to do a quick check to see if it's one that has more than one choice or not. Just do a quick look, quick check. When you're given the name of it, it's kind of easy. Nickel 3. How am I going to write that? It's going to be the symbol nickel. And now what do I put on it? What's the charge going to be, Dallas? +3. +3. It's a metal, so it's got to be plus. And it's telling us the charge on the ion. +3. That's easy. It's like they're telling it to us. If I'm asked a cadmium ion, this becomes trickier because I actually have to find cadmium, and then I got to find out what the charge is. What's the oxidation state of cadmium? Is it +2? Cd +2. So you need to be good with your periodic table. You need to be able to find things, right? I need you to know where, you know, these cadmium is one of these guys here, +2. Got to be able to find it fairly quickly. Okay, let's now put it together and do some compound naming here. We did some compound naming yesterday when we did some Lewis diagrams. These examples are all univalent. It means that the metals all have only one possible oxidation state. It means that I don't need the brackets for this. I just have to name them. This is pretty straightforward business. I've got that ion and that ion. What's this called? Hands up, what do we got? Christopher? Sodium chloride. Don't wait for me. This is as straightforward as it is. Keep going ahead in front of me until I break your concentration to give me an answer. So don't wait for me to do these. Same with any examples we do. Get your pencils out. Go ahead if you think you know, because this is review. Somebody got number 2? Yep, what do you got, Atlee? Aluminum oxide. Somebody have number 3? Yep, what do you got, Chelsea? Yep. Magnesium fluoride. Again, pronunciation, very important to get the correct spelling. I don't really care. Fluoride, but fluoride is the way I have to say it. Dallas, what do you got? Zinc sulfide. Okay? Univalent, no brackets, Roman numerals, don't have to worry about it. Very straightforward. Okay? All right. Let's talk about determining the formulas. So formula of ionic compounds, whether you call it the crisscross rule or the crossover rule, do not write this all out. This is stuff you've done for years figuring out formulas. If you want to make a reference to your text, you can say, see page 90, and it talks about writing the symbol, then write the oxidation state, then cross them over, then cancel out any common factors, bring it to the lowest common factor, write your formula, right? So this is not new. Again, whether you call it, I always called it the crossover rule. The teacher that made this PowerPoint called it the crisscross rule. Whatever you want to call it, it doesn't matter. Again, see page 90 if you ever want to make reference to that. But it's pretty straightforward. I'm hoping you guys, have seen this. Okay, so next slide, a bunch of examples. Again, if you are comfortable with doing this, you can just go ahead and do this. I don't actually need you to write down the oxidation states, but some people do, all right? So silver nitride, and I'll do that one very carefully with everyone. Again, you may know, you might be able to just do the crisscross in your head, look at the oxidation states, get the formula, that's great. That's where I want you to be when we get to a test. I want you to be where you're just doing it in your head and you're not having to actually write it all out. But to write it all out, I've got silver, Ag. What's the charge on a silver ion? Hands up. Yeah, what do you got there, Janessa? +1. And nitride, what's going to be the charge on a nitride? Now, nitrogen has some other options, but I want you to keep your non-metals as just what it is to get it filled. Atlee, -3. So now we crisscross. Here we go. This is the fun part. All right. I don't need to see any of that stuff. This is grade 9, grade 10. I'm hoping you're looking at me going, wow, really? You're going to draw arrows to guide our eyes here? Ag3N, because we don't write the 1. Sound familiar, everybody? Again, review, but we do need to take the time, make sure we're following the proper stuff. So again, you can go ahead. You don't have to wait for me. You're going to give me an answer? Oh. No, because the negative just represents the charge. When we cross them over, it represents the number of atoms, right? And really where this comes from is yesterday's Lewis diagrams, right? From yesterday's Lewis diagrams, if we drew, and it would be hard for a silver because silver's got a bunch of funny electrons, but silver would need 1, and nitrogen silver needs to get rid of 1, nitrogen needs 3. You remember how we did that? That's where it comes from. So the negative charge, as soon as you crisscross it, turns into the number of those atoms of that type. So no negative written in there. It becomes a number. Does somebody have one for zinc chloride? What do we got? Formulas. Don't tell me the charges. I just want the formula for zinc chloride. Yep, Dallas? That'd be a ZnCl2. It's all right. ZnCl2. Okay? Zinc 2, chloride -1, cross them over, ZnCl2. Magnesium sulfide. Yeah, Chelsea? Yeah, very good. MgS. MgS. Now that comes from, and again, I'm hoping everybody knows why it's MgS, but if not, we'll take the time here. Mg is +2, S is -2. We cross them over, right? That puts 2 and 2, but remember, we have to cancel off any common factor. That gets us to MgS. So that goes to 1, that goes to 1, and we have MgS. All right? It is the simplest representation. Yes?
I don't think the folded one was the most common.
What element are you talking about? Sulfide. Okay, so let me go back to the statement again. For the non-metals, I need you to pick -1, -2, -3. And that's because we do not have enough information to tell you why it's anything but -2. So I need you to use -2 for the nonmetals for sulfur every time. All right? We will worry about all the extra numbers for the nonmetals at a later time. Okay? All right? Okay. Let's now talk about multivalent ones. And then we'll mix them all together and see if we can pull them apart. So now we're dealing with the ones with the Roman numerals. It means that if I'm doing a formula and I'm told the Roman numeral, it's easy. But if I'm doing a name and I got to figure out what Roman numeral to use, that's a little trickier. Because there is more than one possible oxidation state, you must indicate with your brackets and your Roman numerals which one you're talking about. This becomes very important in writing reports on, say, a chemical reaction that you are doing. Or perhaps if you're working in a laboratory situation and you're a technician or perhaps an assistant to a technician, and that technician says, I need some iron chloride. You would then proceed to the storeroom where you find your chemicals, and you'll find that there's 2 versions of iron chloride. There would be an iron 2 chloride and an iron 3 chloride. And you would then not know which chemical to return to the technician. So when there's more than one option, you must always indicate with your brackets and Roman numerals which option we're talking about, so it doesn't mix up those 2 different chemicals. Every chemical must have its own individual name to identify itself, to prevent, ambiguity, mixing them up of chemicals, etc., etc. When doing this, it is actually easier than the univalent ones. When we were dealing with silver and zinc and cadmium, you've got to go and find those numbers because they're not in a logical location. With this, they're telling you what the number is. You can actually get the formula easier for these guys because you don't have to go hunting for the numbers. It's given to you. Again, go ahead. Cross them over. Cancel out what you need to cancel out. Don't wait for me. Somebody have an iron 2 chloride? Somebody's got to be done that first one. Yeah, William, what do you got? FeCl2. 2 is given, cross it over. Cl is in group 17 minus 1, cross it back. Beautiful. What are you looking for? You don't need to worry about looking for mercury because we tell you it's going to be the 2. And that's minus 2. So what are you going to get when you cross over? Nothing. Well, you're not going to get nothing, but you're going to write it down as no number, right? But you do need the symbol. That's correct. This is where, and I told you guys at the beginning that normally I gave a quiz on various symbols and names. And this is where you guys are going to be cursing me for not giving you the quiz. Because now you guys are a little out of practice at locating the elements. So you're going to have to get into the practice of doing it. Because mercury, I didn't test you on the symbol for mercury, so now you got to go look for mercury in order to get the symbol correct. There you go. I did a disservice of not quizzing you on the names and symbols. Timing didn't work out. Yep. Yes, it is. Yep. What's the symbol? What is our formula here, Janessa? HGO. Excellent. HGO. So you may think this is easy. You may not want to do the practice problems, but you need to do them if it isn't simply for the purpose of using the symbols. Because when I give you a test, if you felt that the last test was long, and I give you the next test on naming and determining formulas, and you think, hey, this is easy, I know how to do this, I don't need to practice, and I give you mercury oxide, and you don't know the symbol of mercury, and you don't know where mercury is, so you use the tactic of running your finger along every element, and then you do that times 20, because I'm going to have 20 examples on it, you will be not finishing your test. And I will pull it out of your gripping hands. And I will shed no tears. So you do want to practice so that you know that mercury is down there. All right? Next one. What is the formula for gold 1 nitride? Dallas, what do you got? AU3N. Excellent. 3 and 1. Lead 4 sulfide. And what do we got? We got too many, same name here. What do you got? PBS2. Yes, because the 4 went there, the 2 went there, and we cancel off a common factor of 2. Okay? Excellent. Let's keep rolling. Now to go to the name. And there are a couple of ways of doing this. Because now we have to decide, one, if it is multivalent. So you look at the iron and you have to say to yourself, does that have more than one oxidation state? And the answer is yes. The answer is yes for all of these. But when I mix it up, you've got to decide that, right? So again, if you know where iron is quickly, you can quickly take a look for iron. Oh, look, I got 2 choices. I'm going to need Roman numerals for that. The next thing is you got to determine which Roman numerals that you're going to use. 2 ways to do this. And I'm a fan of the second way. The first way we would call the reverse crossover, right? We would, in our minds, bring the charges back to where they originally came from, 3 and 2. But that only works if a number hasn't been canceled away. If something's been canceled away, that doesn't work because we've canceled a number away. In this case, by using the reverse crossover, my 2 goes back up with the oxygen and my 3 goes right there. So this is an iron 3. Okay? But let me show you one other way of doing it, and I like this even better. I'm going to clear this out of the way. It has nothing to do with writing anything down, but it has to do with using your periodic table quickly and easily. I take a look and I see that I've got 2 choices, and I've got iron 2 or iron 3. I know I'm up against oxygen. If it was the 2, what would have happened to my numbers? Canceled away. Can't be 2. If it's 3, in my head I do a quick little crossover. Oh, that's the exact formula that I would have got. So what I actually do very quickly, because I'm good at it, is I go to iron, I look at the possibilities, and I see the only thing that can give me that formula is iron 3. And so I actually make the formula for iron and oxygen depending on which one gets me the right formula. And after babbling away, I've lost my train of thought. What type of iron is this? This is iron 3. So this is iron 3 oxide. Okay? Again, looking at the nickel. There's my 2 choices. It's up against sulfur. Sulfur's right there. What type of nickel must this be? What type of nickel must this be? Yeah, Braden, what do you got? 2. Has to be 2, because it's going to cancel out with the sulfurs too. And I like that way a little better than this reverse crossover, because if you do the reverse crossover here, You're going to go 1 and 1, and if you're not paying attention, you're going to think it's 1. But when you do that, you've got to realize, oh, but sulfur's normally 2, which means we canceled 1 away, which means it's still going to be a 2. That takes a lot of logic. Much easier just to look and quickly do it in your head and figure out which one it is. And again, as I've babbled away, I'm going to scribble that all out. What was this? Nickel 2? Oh, it's nickel. It's not Nicola. All right. Nickel 2 sulfide. Pronunciation is very important for me, especially with words like skizzers and muscles and diaphragm. All those science words with those hidden letters in there. What's that? Oh, pneumonia? Yeah, I agree. All right, what do we have for this one? Again, I'm not going to look. You guys do a quick check. Dallas, what do you got? Chromium 3. Chromium 3. Oops, put an extra one in there. Chloride. Excellent. Next, yeah, what do you got there? Lead 2. Let's take a look. If I bring the 2 up here, right, then the 1 goes up there, but oxygen is normally a 2, which means it had to cancel away. It's got to be the other one, obviously. There's only 2. It's going to be lead 4. It's lead 4 oxide, and that's where the reverse crossover catches you. You look at the lead, you see 2 and 4, and you think, if it was the 2, Haley, if it was the 2, and we did 2 and 2, what would happen to the 2s? They didn't cross each other out. But they didn't cross each other out, did they? So if it was the 4 would go there, the 2 would go there, I'd cancel down to 1 and 2. It's got to be lead 4. So that reverse sometimes gets you. That's why I'm a fan of quickly coming up with the formula. Oh, look at here. I got an O again. O can be tricky. Which one is it? Yep. Yeah, it's mercury 1. Mercury 1 oxide. In this case, the reverse crossover would have worked, right? But you never know, right? So you got to do a quick check. All right, excellent. Let's now mix a few of them up here. Oh yeah, that's just me doing the reverse crossover, and I'm not a fan of that. So let's now mix some of them up, all right? Some of them are multivalent, some of them are univalent. The multi, you gotta have brackets and Roman numerals. The univalent, you don't have to when doing the names. These are obviously determining formula. So go ahead, don't wait for me. I'm actually going to wait for you to finish these, or most of them anyway. And as you're working quietly, now's a nice time to give a little speech. With this stuff, practice makes perfect, all right? The more you do, the better you get. And being able to name and to come up with formulas is the backbone of doing chemistry, because just looking ahead into the future, when we start talking about chemical reactions, I sometimes give you the name and you need to come up with the formulas. Then, as we continue on and deal with the mathematics of chemistry, the starting point for all problems is the balanced chemical equation. So if I give you the names of the chemicals in the problem and you can't come up with the chemical equation, then the whole question falls to pieces, and that great question that's out of 11 marks becomes 0. So naming is important. It's essentially the language of chemistry. So do the practice. All right, speech over. I know some of you aren't finished. That's okay. I'll take a lithium fluoride if somebody has it. Tyler, you got it? LIF. 1-1. Riley's got silver oxide. We have Ag2O. Zinc nitride. Yeah, go ahead. N3N2. Excellent. Next. We got something? Yep, go ahead. CRSE 2 and 2. Excellent. They canceled out. Is that the last one, Chelsea? AuCl3. All right? Those of you who didn't quite get finished, maybe this weekend, as you're watching the Toronto Maple Leafs crush the Ottawa Senators, hopefully. They've won 2. They got to crash soon. Who knows? Anyway, when we hope that they crush them, sit with your periodic table. Look around. See where the elements are. See what the numbers are. Right? Because the quicker you get to them, the faster you'll be able to do it. All right? Okay. Now back the other way. And this is a little trickier. Don't put provide the correct IUPAC name, blah, 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 blah. Just put number 2, name. Name these. Technically, it's the IUPAC naming system, but yes, just name them. Now, at this point, you got to decide which one are going to have Roman numerals or not. Magnesium, group 1 and 2? No. It's not going to have Roman numerals. Magnesium is just, it's got only one possibility. Your transition metals are the ones that you're checking for. So this group, no brackets. This group, no. Same with even group 3 on the other side. These guys in the middle, probably. Zinc doesn't, and cadmium doesn't, and silver doesn't. Those are the special, these are the only ones here, right here in this little corner here. I think they're the only ones that we deal with. The rest of the transition metals have to have Roman numerals. So again, the more you know about your periodic table, where the transition metals are, the quicker you'll be able to do this. Again, when naming ionic, all you have to do is name the 2 ions. The key is that the ones that are transition metals might need a Roman numeral with a number in it to tell us which one. What do we have? Name for the first one. Yeah, Chelsea, what do you got? Yep. Did we already have that? We did, because I said magnesium and then fluoride. And I think it was with a magnesium. One of those is an R, by the way. How about the next one? Yep, we got Joy. Excellent. mercury 2 chloride. Next. Yep, Dana? Excellent. Lead 2 sulfide. Next, William. Silver nitride. Silver nitride. All right. Next, go ahead, Janessa. Chromium 3 oxide. Yeah, I like it. Chromium 3. Sorry. Yeah. This is me. That was me. You're right. That was a Friday moment. I was thinking about the Leafs winning. It's correct. Yep. Yeah, very good. Tin 4 oxide. Tin 4 oxide. Yes. Yep.
Like, if pouring more out, like, I thought it was.
Excellent. No problem. There's a bunch of practice problems. Now, I'm not going to let you work because I do want to talk about the classical naming system, and 6 to 10, and some of those will be like A to G practice. That's the only way you get better at this stuff, all right? And really, you guys know how to do it. It's more practice of finding stuff on here with speed. Okay. Okay, let's exit that one, and I'm just going to keep recording here because I'm going to continue on, which is what is called the classical naming system. Now, this naming system only deals with the multivalent guys on the periodic table. So all we're really learning now, just here at the end, is how to name the ones with the Roman numerals in the classical system. And you might ask, why do we need to learn the old classical system, Lavoisier, hundreds of years old, when we have the IUPAC system, and it works really nice because all we have to do is put Roman numerals behind it and tell you what the charge is. I guess maybe the reason for that is, I don't know, it's about human nature. People sometimes just don't want to give up the old system, right? Sometimes a language has a strange little dialect in one particular part of the country, and that's because those people just keep those, conventions. The classical naming system has hung on, all right? And so you need to be able to, again, if you're working in a lab and someone asks you for ferric chloride, you need to be able to know what you're looking for, all right? And so, unfortunately, the naming system is still around. In our chemical storeroom across the way, well, in the 50s, 60s, and 70s, high school chemistry labs had a lot of dangerous chemicals in them, and they used them, all right? Now, for safety reasons, we've been informed, don't use those chemicals. So we've gotten rid of a lot of chemicals, but there are still some old sources of chemicals that are maybe 20 years old that still have a function that we use very little minute amount, and they have the old classical naming system on it. So you need to know, even now, how to name things in the classical system. Okay. Don't write down the first bullet, all right? I'm just looking at the time, and I want to kind of get rid of this. The classical system was used for metals with have just two possible oxidation states. Don't write down the first bullet. Write down the second one. All the way to the bottom. Second right to the bottom. Now, depending on who your teacher was last year, you may have already seen this. Does this sound familiar? Ferric, ferrous. No? All right. This system with the us and ic ending can be used for any element that has two oxidation states. If the element has a Latin name, the Latin name is used. So for iron, the Latin name is ferrum, and therefore we use ferrum as the base name. So for the low oxidation state of 2, it's ferrous, and for the high oxidation state of 3, it's ferric. And that's just the way it was done. Again, where does the us and ic ending come from historically? I don't know. Chemists, though, sometimes when we have to learn something that we don't know the background for, make a silly little saying. And our silly little saying for this is us, O, low, ic, I, high. Ic starts with I, you think of the high one. Us starts with O, you think of the low one. Okay? Now, the length to this lesson, and I am looking at the time, the thing that makes this a little long is that we need to go over some Latin names for the elements. All right? So I do need this written down. You don't have to draw a fancy table. You really only need 3 lists. The element, the Latin name, and then the ion name. So it doesn't have to be a fancy table. It can just be right beside each other. You can even put iron, comma, ferrum. And then we'll talk about what the ion name is, but I'll let you go right to the bottom. And also, just to save for some time and some confusion, don't write down this Latin name here for mercury. Just write mercury again, and I'll tell you why. Okay, so 2 possibilities for iron is ferrous and ferric. All right? +2 +3. And if you're going on a line, you can put it beside each other. For copper, it's cuprous and cupric. And I think is it 1 and 2? You check my numbers. I'm just going from what I remember. Is it 1 and 2? All right? So when you get a name like cuprous, you still have to go back to the copper and pick the low one. Stannous and stannic. That's one of my favorites. I like that. Stannous. It's good stuff. I should have named my kid Stannis. That would have been funny. No, he wouldn't, but it would still be funny. Oh, Stannis. Okay, let's continue. Put up my 2 numbers for tin. 2 and 4. So Stannis is low, +2 +4. Yeah, I gotta watch what I say about my kids anymore, because all you guys know my kids. Man, I've entered a strange part of my career. Okay, now lead. The Latin name is plumbum. You may giggle about that. It is funny to say. It's funny sounding thing. This is plumbus and plumbic. And it's 2 and 4 as well, I think, isn't it? +2 +4. Okay? That's why people who work with pipes are called plumbers. You've got to put the B in there and you spell it wrong. And that's because the pipes they used to use were lead. But now we know lead is a toxic metal when it gets into the water system, so now we use copper. Cobalt. Now notice it doesn't have a Latin name, so we just keep the regular name, cobaltus and cobaltic. All right? So we can have a Nicolust and a Nicolic. Funny too. It's just funny to say. So if they don't have the funny names in here, then you just keep the regular name and you put us and ending on it. Let's not worry about the charges anymore. I just want to get to the bottom at this point. For gold, we have Aurus and Auric. So you are going to need to memorize these Latin names. Mercury has a funny one. It's called Hg because it's like Harargium or something. I don't even know how to say it. I never say that word. That's where the Hg comes from. But yeah, that's where those symbols are coming from. The symbols that are strange are coming from the Latin names. Yeah. Yeah, that's where our Cu comes from for copper. So for mercury, because, and I don't know why, maybe because no one can actually say this word, they say mercurus and mercuric. Mercurus and mercuric. And antimony is stibnium. Again, like where does that come from? That's where it comes from. Antimony is stibnium, and so that's stibnus. That's funny too. And stibnic. And again, you can check your table for the charges. All right? Now, we're down to, who knows, maybe a minute, because I don't know when the bell goes anymore. There are examples for this, but add that to your homework. I will do the examples with you on Monday to kind of review this. All right? Now, I will tell you right now, though, to force you to do some preparation, I like to have a quiz every day as I do my naming. So on Monday, we will start the class with 5 names and 5 formulas, and you got to do the opposite. It won't include the classical, all right, because I didn't get this kind of officially done, all right? So it won't include the classical, but you can try that homework problem. Even though I didn't do classical examples, I think you can give it a shot. It's not totally out of the realm of possibility, but our little quiz will not have the classical on it, and it'll be 5 and 5. I'll put it on the smart board. You'll just do it on a little piece of paper. It will count for a little bit of marks, just for a little bit of incentive, right? But it forces you to do the homework and get practiced at it, okay?